All right. Hello, everyone. So it's my pleasure to introduce Dmitry Goussev. Dmitry Goussev. He's from Wilfrid Laurier University in Canada. It's in Southern Ontario, close to, well, not very close to Niagara Falls, but close enough. Dmitry got his Ph.D. from the Moscow Institute of Fine Chemical Technologies, which is called the Lomonosov Moscow State University. Actually, it's pretty famous, in 1987. And afterwards, he did some postdoctoral work. And in Zurich with Professor Hans Berke. But the first one was in Toronto with Bob Morris, which are big names in organometallic chemistry, actually. And what I think when I became aware of Dmitry was when I was a graduate student, and I noticed there were some papers from his time as a researcher in a group of Ken Colton in Indiana. And Ken Colton is also a very big name in organometallic chemistry. So he has a very famous background, but he's also done a lot of really outstanding research since he joined the Wilfrid Laurier University. And definitely, I've had a lot of overlap in my postdoc with his research as well. And now we collaborate on a project. So he actually has a patent on some of the catalysts that he made during his time in the Wilfrid Laurier University, and they bring in a bit of money and they're sold on Aldrich. So yeah, it's very practical chemistry as well, not only theoretical. Let's see what else. And one interesting fact is that he's in charge of NMR and Wilfrid Laurier, which includes two discontinued variant spectrometers that he takes care of for the last 15 years. So I think it's very interesting. And if you need help, if you have some questions about how to take care of old NMR spectrometers, you can ask him. But today he'll be talking about a project that is close to my area of research, ruthenium catalysts for acceptorless alkyl dehydrogenation. So you don't need any oxidant to get ester, or ester hydrogenation with hydrogen gas. So I guess that should be enough. And Dmitry?
Yeah, thank you. Usually, first, thank you all for coming. I hope that you should find this talk entertaining, useful in some way. There are three parts. I'm going to start with the introduction. I introduced the catalysts, part 2, to introduce the catalytic reaction, and part 3 is about the mechanism of reaction. So part 1 is going to be about the catalysts, and maybe for the benefit of some students who are less familiar with this subject, I'm going to show some introductory slides. So, first of all, bifunctional catalysts. There are different types. The most important, perhaps, is the Laurier type. But today, the focus is going to be on both Laurier and this distinct type of bifunctional catalyst. So, if you look at the structure, of course, you recognize that they are metal compounds. active in the catalytic hydrogenation reactions of compounds that have multiple double bonds between carbon, not only carbon, but at least one of the atoms in the multiple bonds should be electronegative hetero, such as oxygen, of course, in this example. So bifunctional catalysts are useful for the catalytic reduction of ketones, esters, and so the concept of bifunctional catalysts in metal ligand configuration is quite simple. The historical view is that the non-innocent ligand, and this is the references to that part, the non-innocent ligand directly participates in the substrate activation and in the bond formation, meaning that when you look at the product structure, according to the metal ligand cooperativity concept, is the hydrogen that's bonded to oxygen in the product. It comes straight directly from the acidic, from the non-innocent ligand, and naturally, the hydrogen that we find in the carbon in the product, it comes from the metal. It kind of makes sense. Then, when this cycle is kind of finished, then from the result unsaturated metal 16 electron species, we can the catalyst hydride. The catalyst hydride is regenerated on hydrogens. Hydrogen adds to the 16 electron catalyst to get back to the catalytic hydrogenation catalyst. This is a catalytic cycle, and this is the historical view of the way how metal ligand cooperation works in catalysis. Today, the modern view is that, in fact, this 16 electron species is usually not in the catalytic cycle. So, I think the modern view is maybe that this metal ligand cooperativity is different from what we see here. And I'm going to talk about the mechanisms to get more information later. Okay, then it's time to introduce the Milstein catalyst, which is the central species in this work, in this project. The group of Milstein workers, they developed several catalysts. So there are several Milstein catalysts. So this work is concerned with one of those, with complex 2. You see here on the left side. So this complex is derived from the precursor hydrido-chloride complex, right? Taking the hydrido-chloride complex with base. By looking at the structure of the Milstein catalyst, of the so-called Milstein catalyst, I think you recognize that we're looking at again an unsaturated 16 electron compound, and there's this part is important. You can see that the central pyridine fragment is not aromatic, it's dearomatized. So the Milstein catalyst, of course, has been studied quite extensively. It has activity in a large number of catalytic reactions, hydrogenation and dehydrogenation as well. So examples on this slide, they are examples of reduction of methyl carbonate, methyl formate, amides, urea, carbonates. So I would like to highlight the impressive activity of the Milstein catalyst for the reduction of esters. You can see that the catalyst loading is particularly low in the two top reactions on this slide. This is an important compound, important catalyst. What about the mechanism? Of course, now you are familiar with the ideas of metal ligand cooperation and cooperation. In this case, according to Milstein, his publication in JACS 2010, I quote, the postulated mechanism involves metal ligand cooperation by aromatization, dearomatization of the heteroaromatic pincer core. So in practical terms, of course, it means that when they use the 16 electron Milstein catalyst on the left complex 2, then in the hydrogenation reduction reactions, it should bind hydrogen. It should split hydrogen to give the hydrogenation catalyst complex 3, the dihydride. This subject of significant interest, chemistry, practical chemistry applied, and theoretical chemistry, of course, it's not surprising that seven computational papers were published that looked into the different mechanistic aspects of the catalytic reactions with those complexes 2 and 3. And the computational studies, they fully supported the mechanism. Nothing wrong about this. So this is where really our work started. And it started from the simple observation that complex 3, despite the fact that this mechanism has been well supported, but complex 3 has never been seen. How they have experience, ample experience working with compounds of this type, metal hydrides, metal dihydrides. So I thought, wow, there must be maybe nice small side project. We could easily make this 3, maybe just to contribute into this area. So this is where our work started. It started by an attempt to isolate complex 3, the hydrogenation catalyst. We experimented at different temperatures, at low temperature, -50, -30, at room temperature, at high temperature, at 100 degrees. And I'm going to show you the outcome of the experiments, starting from the experiment at low temperature. When complex 2 was exposed to hydrogen, was dissolved under hydrogen in different solvents such as methyl cyclohexane or ethyl acetate, we used tetrahydrofurane as well. And of course, we expected that the product of this should be that a hydrogenation catalyst 3. But what formed was something different. Complex 4, a dimer. In the proton spectrum, of course, in the hydrides, they have very distinct chemical shifts. So in the proton spectrum, the bridging hydride is at -20 ppm. Then the terminal hydride here at close to -13 ppm. And in fact, something interesting is that there is a relatively large coupling constant, 2-bond coupling constant between those protons. The spectrum is clean. The product crystallized from ethyl acetate, and the structure was established, was confirmed by X-ray crystallography. Well, then next, I would like to show what happens. next, of course, the question is what's going on? Why the dihydride didn't form? So now we do computational work in addition to the experimental work, and of course, computational work, theoretical work can be very useful when you have questions about things that don't exist or you cannot see. So one question was quite simple about the thermodynamics of the reaction that we expected to produce the hydrogenation catalyst complex 3. So the immediate question, if this H2 addition, if it should be favorable or not. And there is no problem. The Gibbs energy reaction, calculated Gibbs energy reaction for this H2 addition to give the hydrogenated catalyst. Hydrogenation catalyst is negative 3.4, no problem. But then, of course, the actual product is complex 4. And when we calculated the energy of formation for 4, the Gibbs energy is even better, more negative, minus 13.7 kilocalories per mole. So it's so much more favorable product that thermodynamically formation of dimer 4 from 2 equivalents of this expected hydrogenation catalyst, formation of the dimer is actually a thermodynamically favorable reaction, significantly favorable. So what is happening here apparently is that the system is under the thermodynamic control. Okay, I'm going to continue. Now it's time to show what happens when the Milstein dearomatized a complex when it reacts with hydrogen at high temperature, at 100 degrees. At 100 degrees under hydrogen pressure, kind of typical catalytic conditions. If you go back to that slide of the catalytic reactions, you could see the ester reduction was at 110 degrees. So this is about the catalytic conditions at 100 degrees. So after two hours, what we obtained was complex 5 as a mixture of 2 absorbable diastereomers. Of course, here I'm emphasizing that complex 5, it has 3 chiral centers, so up to 4 distinct diastereomers could be observed by NMR at PC2. So there are 2 main isomers. The main one was crystallized, characterized by X-ray diffraction, and to the best of my understanding, the structure of the second diastereomer is related by the flip of the hydride to the bottom side, because those are going to be distinct structures because there is no symmetry plane in the complex. Okay, it's useful to look at the phosphorus NMR spectra of the reaction solutions, crude, reaction solution, straight from the flask or from the reactor, actually. And I think you can see that a complex 2 is practically quantitatively converted to 5 in 2 hours at 100 degrees in benzene solvent. Well, replacing benzene by hexane makes a slight difference because now, in addition to 5, we have complex 6 that you should see on the following slide. And the reaction, in fact, it does not require heating. Complex 5 and complex 6, they form already at room temperature given enough time. So I think that one point maybe that I should emphasize is that what is formed from 2 is solvent dependent as well as temperature dependent. And you will see that this is going to be important later on in this slide. Okay, so complex 6, the crystallized, characterized, is a dimer of somewhat complex structure. So to help you get a better sense of the structure, I would like to emphasize that the bottom fragment, ruthenium fragment, it has that ligand structure on ruthenium. You can see that the pyridine, central pyridine, is hydrogenated, but there is still that remaining carbon-carbon double bond in the fragment. And then the top fragment is again is interesting because now it's the pyridine that on the left, the outer fragment in the ligand is this one that we see hydrogenase. And again, this is something that is going to be important later on. So what we can say is that when 2 reacts with hydrogen, then the central fragment of the ligand is reduced, hydrogenated, preferentially, to give 5, and the one fragment is kind of 6. But then the reduction is not 100% selective, and the outer ring, it is hydrogenated. It undergoes hydrogenation, although to a lesser extent. And of course, when the reaction of 2 with hydrogen is conducted at room temperature, not high, not low, at room temperature, given some intermediate reaction times like 2 hours, in this case, then the NMR spectrum is of this reaction solution. In benzene, it shows like a soup of species. I think today we can say something about most of the resonances in the hydride region. Of course, everything is in the hydride. Like the main part here, the broad, those 2 intense broad resonances are from that dimer 4 that we saw forming at low temperature already. The NMR spectra are 4. They become broad at room temperature. They go back there. This is reversible. They become sharp again at low temperature. We don't know what is the mechanism that is responsible for this broadening of the spectra, but at room temperature, those resonances are broad. We know the chemical shifts of the hydrides of complex 5. There are 2 diastereomers, 2 hydride resonances. We know the chemical shifts of the hydrides of dimer 6. So there is a small contribution from dimer 6 to the spectrum. I don't know what kind of species produced that broad resonance near 11 ppm. And then, of course, you can see that we have here on this side, we have sharp doublets 4. And those, they should be interpreted as due to intermediates because they disappear later in the reaction. Those must be intermediates. And something that we did is we asked the question about what kind of intermediates could be expected upon addition of hydrogen to complex 2. And in fact, there are 14 distinct intermediates that could form, that can on paper. And we calculated the reaction, Gibbs reaction energies for the formation of those 14 intermediates. And interestingly, it happens that only 2, here we have 2 diastereomers of that structure, and we have 2 diastereomers of this structure. So only those structures, both as pairs of diastereomers, only those structures, they have negative Gibbs energies of formation according to the DFT calculations. So it's kind of tempting to say, oh yeah, those intermediates, they probably have the structure that you see here on this slide. Well, I'm going to continue from this and something that is interesting and should become important again later in this talk is the ligand structure that you see here on this slide shown in the upper left corner. The ligand structure where the outer ring is hydrogenated, you know, it forms as a minor byproduct from the Milstein catalyst. So we wanted to make this. We wanted to have this, to know the properties of ruthenium complexes with this ligand. So we engaged in the synthesis of complex 7. I think complex 7, of course, you can see is hydrido-chloride with this ligand that we can use in catalysis. And what helped was that the key intermediate here, 2-methyl-6-piperidininyl pyridine. So this key intermediate, in fact, it was reported, the preparation of this was reported in 1968, and we could successfully reproduce the preparation. So it works quite well. And from this intermediate, it's kind of straightforward, making the ligand by reacting the organic intermediate with diethyl chlorophosphine in the presence of 2 equivalents of LDA. 2 equivalents is essential, critical, which should not be, 1 equivalent should not be used. And then with the ligand, the classical way of making complexes of this type is by displacing triphenylphosphine from this convenient precursor by heating in the solvent. So the complex 7 was made. And in fact, this complex 7 is the part of the work that is still in progress. So we still have questions and we still have some work to do. This is what we know so far. So complex 7, once again, by looking at the structure, you should recognize the presence of 3 chiral centers. So up to 4 diastereomers could be observable in the protons, in proton and phosphorus NMR spectra. In the phosphorus spectrum, we have 2 distinct signals. In the hydride region, again, we have 2 prominent signals, but maybe, again, if we look very carefully, maybe there are other 2 of the 4 diastereomers. One of the structures crystallized, it was characterized by X-ray diffraction. You can see the structure of this compound. Now, if you read the title, of course, this slide is about hybrid Laurier-Milstein-Type complex. And this is, of course, because if you look at the structure here, you see that there are 2 weakly acidic groups in the ligand. NH is like in the Laurier catalysts, and this CH2, the group, is like the weakly acidic group in the Milstein catalysts. So then the question, of course, is what should happen if the compound, if the hydrido-chloride complex, if it should be treated with base? According to the DFT calculations, the deprotonation of the nitrogen group should be more favorable, and the dearomatized structure is less favorable, about 1.9 kilocalories per mole higher in energy than the amide form. In experiment, and we did 2 experiments, we treated this complex with potassium terbutoxide in one experiment in tetrahydrofurane solvent. And in the other experiment, we used a different base, sodium bis-trimethylsilyl amide in benzene. And I think you can see that the spectra, they look similar, but obviously they don't display like single species or like two diastereomers. They display too many signals. So this is again something that clearly something else is going on. More than one product is formed, and this is something that we continue working on. Again, something that we should hopefully know more about. The last compound complex that we are going to see in this work, you're going to see in this work is the Milstein-Type complex 8 derived from phenanthroline. The preparation is straightforward. We add this methyl group to phenanthroline, then to that methyl group, we add the phosphorus group, again, by reacting the methylphenanthroline, by reacting it with diethyl chlorophosphine in the presence of two equivalents of base. So the product formed is practically quantitatively, and the methyl complex product 8 is formed almost quantitatively. Again, following the usual way of making such compounds. The structure of complex 8 is, as expected, uneventful, regular, octahedral. There's nothing special about this. Now, when complex 8, this precursor hydrido-chloride, when it is treated with potassium tributoxide and tetrahydrofurane, as expected, as it could be expected, we obtained the dearomatized complex 9. The structure of this compound is on this slide. The NMR, proton NMR is clean, consistent with the structure. There's nothing special or unusual about this compound. Now, of course, one reason to make 8 is to check the reactivity, because the related Milstein catalyst complex 2, dearomatized complex 2, is hydrogenated under hydrogen. So the question if complex 8 is susceptible to hydrogenation, and in fact, the pincer ligand of 8 is readily hydrogenated under reducing conditions, even simply dissolving dearomatized complex 8 in ethanol. It gives within 2 hours, 3 hours, within hours, it gives the product mixture of complexes 9 and 10. The structure is different in that sense that in 9, they have the outer ring hydrogenated. In the structure of 10, we have the other ring hydrogenated. The outcome and the product composition depends on the reaction conditions. In fact, both 9 and 10, they are not soluble in ethanol, so they crystallize conveniently, can be easily isolated by filtration. So when the material that crystallized in an NMR tube, when it was analyzed, they saw almost like a single product 9. But then when we attempted a larger scale preparation of 9, we found that the material that crystallized from the flask, it was a mixture of 9 and 10. Well, and of course, not only ethanol, not only by dissolving in ethanol, the dearomatized complex 8, it undergoes hydrogenation under hydrogen at 100 degrees. 4 hours gives that product, quantitatively product. The product 11 is a mixture of 4 diastereomers. Of course, they are not all the same in terms of energy. This 11A is the most stable, the main diastereomer, and so we calculated, and those other 3, they are higher in energy, but not very high in energy, so they're absorbable by NMR. So the phosphorus spectrum, it shows those 4 corresponding phosphorus peaks, and when we crystallized the product, it crystallized as a mixture of this 11 and 11C that you see as disorder in that part of the structure. So there's some intermediate, we reached the end of part 1 about the catalyst complexes, and some intermediate conclusion is that clearly ligands possessing an N-heterocyclic backbone, they are non-innocent under reducing conditions. And there are related examples. It's not just something that we found. There are related examples in the literature from the work of Milstein, from the work of Susumu Saito, who is at Nagoya University. And you see that related tetradentate and bidentate ligands that contain a heteroaromatic fragment, they undergo reduction under different conditions, reducing conditions. Again, so this is something to keep in mind that, well, if you're working with ligands of this type, and if working under reducing conditions, such as in catalysis, then this is something to keep in mind when you think about the mechanism. Okay, now it's time to talk about catalysis. So part 2 is about catalytic ester reduction. We have certain objectives in this part. Objective 1, we have those complexes. So I think that the obvious question is, well, what are the differences if they are catalytically active? What are the differences? Do we have more efficient? Do we have less efficient complex? So we're just interested in the relative catalytic activity of the complexes on this slide. I would like to emphasize that we have this complex 7. We do not yet have the presumed active form of the hydrogenation catalyst that, again, presumably forms from 7 when treated with base under hydrogen. So we cannot, at the moment, we cannot test 12, but of course we can test 7 with base under hydrogen. And then we have those complexes 5, 6, 8, and 11 that, of course, are all available. So the second objective, of course, is to look into the question if metal ligand cooperation by aromatization, dearomatization, if it plays any role in ester reduction with the Milstein-type complexes 2 and 8, with those 2. If those 2, if they can do catalysis by metal ligand cooperation involving aromatization, dearomatization. We don't need many substrates at this time. The question is really very specific. It's about the relative catalytic activity. So we selected a typical ester, such as methyl hexanide, for testing. And understandably, that when methyl hexanide is reduced, the product should be hexanol and methanol. So we work under kind of standardized reaction conditions, catalytic reaction conditions. All catalytic reactions we do in 300 milliliter stainless steel par reactors stirred at the same rate. This is important. Our reactant is gas, and it's not unusual when reactions with gases, they can be limited by the rate of transfer of gas into the liquid phase. So the rate of stirring it can be important. Anyway, the ester is the methyl cyanide. We take 0.2 moles in the reactor, and this is almost exactly 26 grams, significant quantity. We're not working on kind of micro scale. We pressurize the reactor to 50 bar hydrogen pressure and then disconnect the source of hydrogen. So then, of course, in the reaction, we should see how the hydrogen pressure drops as the reaction proceeds, as the hydrogenation proceeds. Methyl hexanoate is a liquid under normal conditions, so we don't really need a solvent. So we don't use solvent just to keep things as simple as possible, because this is quite important when it comes to calculations, modeling. Because on modeling, you would really like to keep things as simple as possible, meaning working at room temperature, no solvent, or anyway. The catalytic experiments here, they were done using 5,000 to 1, some 10,000 to 1 substrate to catalyst ratio. In quantities of the ruthenium complexes, this is about 20 milligrams with 5,000 to 1 substrate to catalyst ratio, or 10 milligrams when 10,000 to 1. We take the catalyst on an analytical balance, accurate to 0.1 of a milligram. So we have about 1% error in the catalyst amount here. The reaction times, 24 hours at room temperature, and those reactions are relatively fast at 100 degrees. So at 100 degrees, we need only 3-hour reaction time. Of course, experiments, they were repeated 2 times to 3 times, most 3 times, to ensure that everything we do is reproducible. Something to mention is that the reduction, catalytic reduction of methyl hexanoate, when incomplete, is always accompanied by formation by transesterification and formation of axial hexanoate. So this is something that you should see in the proton spectrum, and all conversions, that all numbers that I'm going to show, they obtained from the proton NMR spectra, quantitative proton NMR spectra. Here is just a typical representative proton NMR spectrum at a relatively high conversion. So we can see the peak of methanol. We can see the triplet of the CH2 group of hexanol. You can see a small amount of unreacted substrate. Then here, near 4 ppm, we actually see the product of transesterification axial hexanoate, the CH2 group of that. And the last one is near 2.3 ppm. We have 2 triplets, 1 triplet from the substrate, and 1 triplet from, again, the product of transesterification. To calculate the yield, or sorry, not the yield, conversion, we take the integration, use it in a meaningful way. So from this spectrum, for example, we calculated 93% conversion of ester to hexanol, 4% conversion of ester to axial hexanoate, and of course we are left with a small amount, 3% of unreacted ester. The balance is 100%. Okay, so I'm going to start by acknowledging the results of testing with complexes 8 and 11, those phenanthroline, dearomatized phenanthroline, and the product of hydrogenation of this, maybe for the relatively simple reason that those complexes are inactive for the reduction of methyl hexanate. So no catalysis. And of course, even when you face such kind of negative results, no catalysis, yeah, I think it helps to know why. If you're involved in catalyst development, you may want to know why things work and why they don't work. So in this case, the reasons are apparently different, more certain for 11. On the following slide, I'm going to explain why 11 is inactive. Less certain for 8, but there is still some considerations. So first of all, for complexes to be active in hydrogenation reactions, they must bind hydrogen. So the question is, if this complex, if it can bind hydrogen, well, according to the DFT calculations, theoretically speaking, this should not be a problem. So that potential theoretical hydrogenation catalyst 13, yeah, it has a negative Gibbs energy formation, could be formed. Well, the trouble, of course, again, is that like with the Milstein catalyst, you remember exposing the Milstein catalyst to hydrogen gives complex 4, and complex 4 formed and crystallized from ethyl acetate. So we looked at the energy of formation of the corresponding related dimer from 8. And once again, we see a more negative, more energy of formation, more favorable species. So first of all, I'm going to say that, complex 13, the catalyst that could have worked, it just doesn't form, apparently. But then complex 14 that forms, they expect to form, it's like complex 4, but complex 4 was formed and crystallized from ethyl acetate. It means that complex 4, it cannot be or shouldn't be active toward the reduction of esters. So complex 14 apparently is just like 4 is inactive for the reduction of esters. Now, complex 11, of course, is a mixture of 4 diastereomers. And once again, the question, if from the 16 electron 11, if we can make the hydrogenation catalyst, if we can add H2, and the DFT reaction energies are all relatively large, positive. So I think the simple practical point, we can say that complex 11 is inactive because it cannot bind H2. So with those Gibbs energies of formation, the concentration of the hydrogenation catalyst is 0, practically 0. So the complex cannot bind H2, and it would not be able to transfer hydrogen to the substrate. And maybe as simple as that. Okay, so it's time to look at the more interesting results with complexes. So of course, this is our starting point in the project. This is the Milstein catalyst, active. We know it's active from the literature. And of course, it's time to look at what we get with 2, what we get with 5. And at 100 degrees, we get descent to 1,500 turnovers with 2. And even better, 6,000 turnovers with 5. You recall that 5, it forms from hydrogen from 2 under hydrogen at this very temperature in 2 hours. So kind of makes sense to say the catalytic activity of 2 might be due to formation of 5. Everything looks like logical, relatively straightforward until we tested this reaction at room temperature. And now at room temperature, we suddenly see the reverse. Now the Milstein catalyst gave 3,600 turnovers, and complex 5 only 1,700. So something else clearly is going on. And on the following slide, I think I can explain what, I mean, to some extent, we understand what might be going on. So here, we're looking at the reaction progress with complexes 5 and 2. So with complex 5, the less efficient at room temperature, I think you can see that the reaction started at a good rate. Well, slow it down, reached 13.5 bar hydrogen pressure we had consumed at the end of the reaction in 24 hours. But this is it's interesting with 2 that there was very little, if any, reaction at, within the very first hour of the reaction, and only at this point, 1 hour after, like looking at the reactor, nothing is happening. But in 1 hour, suddenly the reaction started, and it should. And of course, at the end, in 24 hours, we could see 26 bar of hydrogen pressure consumed in the reaction. So way more productive. Okay, when looking at cases like this, of course, something we can say is that there's something that we can say is that induction period with complex 2, it suggests certain things. That complex 2 itself has low or maybe even no catalytic activity. That during that time, the first hour, some unknown active catalyst X is formed from 2 and starts working from 1 hour reaction time. I think quite clearly that this unknown catalyst X must be way more productive than 5. And something else, because of the differences in the reaction rates at 100 degrees and at room temperature, we can propose that formation of this very active catalyst X is probably suppressed in some ways at 100 degrees, but the formation of this catalyst is more favorable at room temperature. So we should look at more at the results with dimer 6 and dimer 7, complex 7, to get more information about. I'm afraid I'm going over time. To get more information about, and something that I think you can see immediately is that, okay, they had good turnovers with 2 and 5 at 100 degrees, but now with 9, it's even better. Also, at room temperature, again, we had good turnovers with 2 and 5, but even better with complex 6. And then with complex 7, it's really the most productive catalyst in this group that gave 9,000 turnovers at room temperature. That ligand structure is in the dimer. So if it's split under the catalytic conditions, then what we should get that complex 12, the dihydride. That, of course, theoretically speaking, we expect to form from 7, this base and under hydrogen. So I think at this time, they propose the idea that we have is that this complex, it forms at room temperature from 2 and is responsible for the catalytic activity that we see. There is something interesting about the composition of the reaction solutions, the catalytic reaction solutions. So we took samples straight from the reaction solution, catalytic reaction solutions after 4 hours at room temperature, because we're checking if there should be some additional reactivity, catalyst decomposition, transformation. What we find is that with 7, of course, 7 itself, it shows 2 phosphorus peaks in the spectrum. And when deliberately treated with base in alcohol, they see formation of the alkoxide 15 that shows 2 phosphorus peaks in the phosphorus spectrum at the chemical shifts that we see in the catalytic reaction solution. So we're quite confident that those 2 peaks here, they belong to diastereomers of the alkoxide 15. Alkoxide, because can be methoxide, can be I don't know if there is there are ethoxide, butoxide, propoxide, hexoxide. I don't know. Okay, then so we have no catalyst degradation. In fact, the reaction in 4 hours is complete, 100% conversion. So we have the alkoxides in a 1-to-1 product mixture of hexanol and methanol. With 5, we have a single species in the product, in the catalytic reaction solution. Of course, not the same ester conversion, so only 47%. No catalyst degradation, because we know that peak belongs to the ethoxide 16 that can be independently synthesized. And now the last is complex dimer 16, which I think clearly in the catalytic solution, it's split to give the 15 and 16, maybe something else. But okay, so then the question that maybe, well, if you're interested in the mechanisms, the question that you're going to have is, okay, if those species that we see in the catalytic solutions are alkoxides, in the catalytic reaction, the catalyst, hydride or dihydride, like 12 or 17, they somehow should form from the alkoxides. Is this feasible? According to the calculations, the reaction of alkoxide converting to the hydride under hydrogen pressure, those reactions are, well, definitely feasible for 17, little less for 12, but there is no huge problem. Of course, something that we noticed that this is our more efficient catalyst, and 12 is the less efficient catalyst. So that the result, clearly, the energies, they suggest that the concentration of the less efficient catalyst, 17, should be greater than the concentration of the more efficient catalyst, 12. So the reason why 12 is more active, it must be due to faster ester reduction, despite that lower catalyst concentration. Some intermediate conclusions is that, well, the best for ester reduction is complex 7, which is presumably pre-catalyst to the highly efficient hydrogenation catalyst dihydride 12. And of course, that 12 in a catalytic solution we expect to exist, must exist in equilibrium with the alkoxide 15. And again, we can speculate that the room temperature reduction conditions, they favor formation of 12 from the Milstein complex, and at 100 degrees, the formation of 12 appears to be suppressed in favor of 18. And I don't have many slides, but hopefully I can tell you a little bit about the mechanism of the reaction. What's interesting about this is that we have the two catalysts, 12 and 18, different in the ligand structure. And we know that, well, this is more efficient, more productive, and this is less efficient, less productive. So can we explain the differences by doing calculations? Because we would like to see some theoretical difference. Okay, first of all, let's address the point of catalyst hydrogenation, catalyst formation. What we put in the catalytic solution is this, the 16 electron complex 4. So to get the catalyst, we have two pathways. One is the direct pathway. H2 adds to give the dihydrogen complex. Then the dihydrogen complex, it can be stabilized by a molecule of alcohol. In the calculations, we model this by ethanol. By the way, it means that we are looking at what is happening in the catalytic reaction when already some alcohol is formed, not at the 0 point when there is only ester and no, but already when some amount of alcohol. And of course, this is the main part of the catalytic reaction when some alcohol is already present. Okay, so and then we have this shuttle process that gives the catalyst dihydride. Oops, wrong way. But then there is this different reactivity that should be considered. Is the reactivity of 4 toward the alcohol when it's present in the reaction solution. Because alcohol can compete, it does compete with hydrogen. And it can add to ruthenium to give the alcohol complex, ethanol complex in this case. This ethanol complex can protonate the nitrogen of amide nitrogen to give the alkoxide. And the alkoxide, it can be stabilized by hydrogen bonding with a molecule of ethanol. And I think what you can see immediately is that, first of all, is that right from the start, the alcohol complex is much lower in energy. So the formation of the alcohol is more favorable, but not only thermodynamically favorable, kinetically favorable as well. Because here, the protonation is at transition state is at 7.7 kilocalories per mole. But to get to the product through the direct pathway, we have to overcome this barrier, which is at 15 kilocalories per mole. So I think we can say that the 16 electron complex 4, it adds alcohol much faster than it can add hydrogen. And of course, we have to propose that the dihydride catalyst forms somehow from the alkoxide, not from where we started. So how this can happen? Again, we calculated the way how from the alkoxide with hydrogen, how we can regenerate the catalyst. So the starting point is the alkoxide stabilized by hydrogen bonding. It can rearrange into this agostic ethoxide structure. This is a relatively low barrier process. And the product in the intermediate is not at a very high energy. Then hydrogen can displace the agostic CH, because obviously agostic bonding is weak. So hydrogen can displace the agostic CH to form the dihydrogen complex with the alkoxide stabilized by 2 hydrogen bonds. And from this point, of course, we know that H2 can be deprotonated to give the catalyst. Something to mention is that this interesting intermediate, in fact, is connected with the dihydride by aldehyde, acetaldehyde insertion into one ruthenium hydrogen bond. So from the practical point of view, here we'll learn something about the catalytic conditions that the alkoxide complex of an efficient catalyst, it must be labile to regenerate the catalyst. Okay, then we know the stability trend. We know that methoxides are most stable. They're more stable than ethoxides, butoxides. And then we know that primary alkoxides are more stable than the secondary alkoxides. And of course, tertiary alkoxides are the least stable. So then it's not surprising that, of course, in practice, we know that the reduction of ethyl esters is typically faster, much easier to do than the reduction of methyl esters. It's because with methyl esters, we get methoxides, and those are more difficult to regenerate into the catalyst. And of course, something else that we know is that catalytic reduction of ketones is less challenging than the reduction of aldehydes and esters, simply again, because the catalyst is easily regenerated from the unstable alkoxides. 2 more slides, 3 more slides, actually. So this is the catalytic cycle. And from the catalytic cycle, of course, this is the catalyst, dihydride. Ester, our model is for hydrogenation of ethyl acetate. So ester inserts into the top metal hydride bond. So here we have the product of insertion, the agostic ethoxide. Well, then this is the critical step, step 2, because that agostic ethoxide, it should rearrange. The agostic CH is displaced by the oxygen of the ethoxy group. So here we have this now oxygen bonded, and the H is not bonded. So it is this structure that, in fact, it has some kind of unique property, is because in this structure, that carbon to oxygen bond that we should break when we reduce esters, it is that carbon to oxygen bond that becomes extremely weak. So weak that, in fact, it breaks, the breaking of the bond is practically barrierless, meaning look at the energy of this intermediate, and the transition state is only at 21.9 kilocalories per mole. So this, the breakage of the bond it costs almost nothing. So then, of course, as a result, the aldehyde is eliminated, and we get the product alkoxide that we saw on the previous slide. And from this alkoxide, of course, we know how the catalyst is regenerated by displacement of the alkoxide. We have the dihydrogen intermediate, and then we have the catalyst regenerated. And the catalyst regenerated takes care of the aldehyde. It's going to, we have insertion of the aldehyde, and eventually the cycle is closed. So practical points that the NH group is not directly involved in the reaction process. NH is a direct group. And the second important point is that the 16 electron unsaturated complex is a pre-catalyst. It's not in the catalytic cycle. So there is no metal ligand cooperation in the classical sense. And when we look at the 2 catalysts, the more active on the right, the less active on the left, something that we see 20 kilocalories per mole on the left, 16 kilocalories per mole on the right, 24 kilocalories per mole on the left, 19 kilocalories per mole on the right. So I think you get the point that with the more active catalyst, the insertion splitting the important part where the ester is involved in the reaction, that works through much lower barriers, should be much faster. So anyways, the final conclusions, we found no evidence for metal ligand cooperation by aromatization, dearomatization. So it's best to view the Milstein complex as pre-catalyst, and of course 8 that is completely unreactive. And complex 2 is something that should be an extraordinary catalyst for ester reduction that we should make, that can make this a viable process at room temperature with good substrate to catalyst ratio. And of course, this is the subject of continued research in our group. And I should acknowledge, of course, the contribution of Dr. Daw, who is my colleague at the university. And we have a very nice collaboration with Dr. Eugene Paskin and Daria Sherstikova, who is a student in this group at Okinawa Institute of Science and Technology. Of course, we have some funding. So thank you for staying all this time. Sorry for going over time. And if you still have some questions, I can take questions.
In the interest of time, I'm not sure there's anyone on Zoom, but if you have any short questions, Dmitry is going to be here for another month. But I saw there's a question.
I have a really short question if you have time. I'm not sure.
Why not?
On slide 10, you have phosphorus NMR, and you have explanation for everything except 2 peaks. So what are those peaks?
I think there must be a more efficient way to navigate.
Type 10.
Yeah. On slide 10.
Yeah, on the lowest one, it's like 2,
Yeah.
5B, 5A, and 6.
Those remain unidentified. If you look at 6, of course, there are 2 different fragments. In the phosphorus spectrum, they produce 2 peaks of equal intensity. So something kind of interesting about this is that the intensity seems to be equal. So maybe, just maybe, this complicated structure, maybe it can form a different isomer somehow. So I suspect that, so this is not like a unique structure. I suspect that maybe what we have at room temperature is maybe another dimer structure, but we don't know.
Kind of another isomer.
Yes, again, suspected, but not known or established.
Curiosity, I don't know if you mentioned before and I missed that, but did you observe any time the hydrogenation of the both pyridine rings with strong conditions? Or you never observed the hydrogenation?
Not with ruthenium.
Okay.
There's some work that we did with osmium, and I mean the same system, just osmium metal. And with osmium, under some forcing conditions, like I think 160 degrees, if I remember correctly. With osmium, yes, you can push the hydrogenation to give a fully hydrogenated product.
Okay.
So in principle, yes, not with ruthenium.
Okay, one more question.
Slide 17.
Mm-hmm.
So why is this difference due to scaling, or why that's in NMR tube?
You know, the difference is just in, of course, there is a difference in the way how the reaction, how we did those. Is that top reaction that gave complex 9 was in an NMR tube. I saw the material that crystallized. So we saw the material, we decanted ethanol, dried, the crystals redissolved, and in the spectrum 9 was the main, like 95. There was just a trace of C. Well, of course, that was kind of encouraging. And we thought that, well, you know, this is maybe something we should produce on a larger scale. So the experiment was repeated on this 1.5 gram scale. And again, the product crystallized nicely, no problem. But when redissolved and we collected the protophosphorus, we collected the spectrum that, of course, indicated a mixture. So why? I'm not exactly sure. I mean, it's not unusual. In fact, it's not unusual in chemistry when experiments conducted at different concentrations and different loadings, when they don't work the same way. It's for this reason. So again, it's not something that I find really striking or surprising. It happens. It is for this reason that, for example, I personally dislike micro-scale chemistry experiments, because if you find something useful in the micro-scale experiment, you never know if it can be scaled up to give you some practical, useful application. But again, this is just my reaction.
Yeah. Oh, okay. One more question.
So I have a question about ligand design. So have you tried to investigate if changing alkyl groups on phosphine arms would influence stability?
That's a good question. In fact, a very important question. And when I think about what to do in the fall when I get back home, one of the things that I would like to do, I would like to know how the catalytic activity should be affected by using more bulky, like adamantyl groups on phosphorus. Because again, my intuitive feeling that can be completely wrong is that this chemistry, the catalytic reaction might be faster, more efficient if the groups on phosphorus are bigger than T-butyl. Kind of counterintuitive, and I cannot defend this, but yes, I'm interested. This is certainly a question that should be asked. It's a very important question, and there is certainly must be a way of maybe gaining additional efficiency by using maybe a more appropriate substituent on phosphorus. But this is as much as I can tell.
One more comment. I was thinking about if make phosphine arm more of a scepter by using perfluoroalkyl substituent like Roddick did, example. Maybe it would help to stabilize hydride species.
I don't know. My concern in general when it comes to catalyst development and design in this area, my immediate concern is about the stability of the alkoxide, alkoxide species that can form in the catalyst. So what we don't want those to become more stable. We want those to be less stable, one way or another, some way less stable. So maybe this is the reason why I'm thinking that with more bulky groups, maybe we can actually, it should be easier to displace the alkoxide intermediate by hydrogen to faster regeneration of the catalyst, maybe. But of course, this is still very, very. So really, the question of what kind of group should work better in catalysis, I think it's maybe something at least that comes to my mind is the kind of question that I can ask in return. How that group is going to influence the stability of the alkoxide. So if you have a way of prediction, and if you can tell me that certain groups on phosphorus should make the alkoxide less stable, that would be interesting.
Okay, I think let's end it here because we already went a lot over time and Ayuma has to set up his sample on X-ray. Thanks once again to Dmitry for the talk. Lots of questions and he'll be here for another month.
Thank you.